so welcome everybody. It's now a great pleasure to have Tom Faulkner here, and he's going to tell us about intro to one-dimensional algebras. Tom.
Yes, okay, great. Thanks a lot, Onkar. Thanks for inviting me and having me here. So I'm going to give 3 lectures, and roughly the topic is operator algebras in quantum field theory and gravity. The plan, is today we're just it's basically a math lecture. So I'm sorry, apologize for that, but that's how it is. And then on Thursday and Friday, I'll talk about operator algebras in quantum field theory and then in gravity. I think this is actually a very ambitious plan, so I'm not sure that it might evolve as we go along, but that's the initial plan. I've teased a little table here. We'll fill this table out sometime in this lecture, hopefully. So hopefully the things in this table that we'll fill in, you'll understand, you'll be familiar with at the end of this lecture. Okay, so let me start though with a little bit of motivation. So I think it's fair to say that quantum information is a very nice new perspective on quantum field theory, fairly new. It's a new perspective on quantum field theory, ADS-CFT, and quantum gravity. And really it's sort of a shift in perspective. So, you might have, well, I guess you young people don't remember these days, but you might remember when people were calculating correlation functions and S matrices. I guess people still do that. But now, there's a new perspective where we look at a quantum field theory, for example, and we look at the entanglement entropy of some region in quantum field theory. And to define that, it's sort of blind to the specifics of the quantum field theory, like the field content and so forth. And so, it brings new powerful results. You get, new results about, you can prove sort of non-perturbative things about the quantum field theory and so forth. So this is a nice new perspective. But, the way that we've been doing it a lot recently is just sort of computing entanglement entropy or something like that. We find that it's UV divergent. For reasons that I'm sure you heard about in the last lecture. And so we might regulate it and try to compute some UV finite quantities. Right? So there's various quantities that are UV finite, like relative entropy, mutual information, and so your goal is usually to compute those things. But maybe this procedure that I just outlined is not optimal, because we started with something that's UV divergent. You use that to calculate things that should be UV finite. So maybe we can just go directly to the answer. And the idea is that, there is a way to do that. And there's a sort of a more optimal way to think about quantum field theory from this perspective, from the quantum information perspective, and that is via algebraic quantum field theory. So that's an old subject, but it's really, I think, the natural home for this. It's also interesting to note that operator algebras were also the original home for many results in quantum information. So if you look at some old results in quantum information, you'll notice that they're in the language of operator algebras. So if you've read any of Petz's papers, old papers, then you'll know what I'm talking about. Okay, so that's sort of motivation. So with that motivation, let's just jump in. And start just really simply. So we're going to start with just finite dimensions, and in particular, we're going to think about some observer, say Alice, who has access to some Hilbert space, HA. And so we're in finite dimensions. So this is the dimension of this thing is some finite. Some integer k. And to describe the state of Alice, we need to introduce a density matrix. So we'll look at mixed states. And we have some density matrix, D. So this is a positive operator whose trace is 1. And with that, we can compute expectation values of any observable that we like, okay? So we write the expectation value of some observable that Alice has as just the trace over the Hilbert space in question, HA, times D of times A, right? So that's how we compute expectation values. Now, we started with this density matrix. However, another perspective on this is just to think about this map itself, which this equation gives you a map between A, which is some observable, and some number, okay? And it turns out that that completely determines the state, okay? So we can just shift perspectives and think of a state not as this density matrix, but just as a map between observables and numbers. And these numbers could be complex. In particular, yeah, okay, good. Good, so this is called a linear functional. And so my states will be these linear functionals, and they satisfy some properties. For example, if I feed in a positive operator, that'll denote A plus, then I should get some number that's positive, okay? A positive. And it should be linear, right? So now the observables that I'm thinking about, in this case, turn out to be just all linear operators on this Hilbert space, hey. So the observables are just linear operators, all linear operators on HA. So you can denote that for now L of HA. Maybe you're used to thinking of Hermitian operators as the observables. It doesn't really matter. I can add a Hermitian operator plus I times the Hermitian operator, and I can get any operator in that way. So let's just talk about all operators. In particular, I can reconstruct the density matrix if I use the observable, which is just this Dij matrix elements of this, if I just use the observable Ji, okay? Okay, good. So firstly, some things. So the space of all linear operators is an algebra, okay? So that's where operator algebras are coming in. In fact, it's what's called a star algebra. Right, so that just means it's an algebra, which means that if I have two such observables, I can take the product, and I can take linear combinations, and I can take its Hermitian conjugation, right? That's what the star refers to here. And they're all in this algebra. Okay, good. So this is, I think a shift in perspective where in some sense we're sort of now focusing more on the algebra, okay? Instead of the state, we're focusing more on the algebra. Okay, so now once we have this, it's useful to think about purifications, as we know. So purifications. So in particular, we think about some extended Hilbert space where we have some environment. So my Hilbert space is HE, tensor HA. And I can, think about some pure state in this total Hilbert space, and I'm trying to find some purification of rho, okay? So psi is some vector in H. And in particular, the algebra of operators, this L of H, sort of embeds into the algebra of all operators on this guy, which is denoted L of H, as follows. I have to go over here now. So in particular, we define a map, pi of A, which just includes the identity on the environment, tensor A, okay? And so this is a subalgebra of all possible observables on the Hilbert space, which is just L of H, okay? And in particular, psi is a purification if when I take psi and I feed in operators A, psi, like this, I just get back my original linear functional. So that's what I mean by purification. And in particular, then, you can go ahead and you can compute the density matrix using this method. And, as you've done in undergrad classes, you find the answer is just the partial trace of psi. Okay. Okay, good. Now, if we think about this sort of purifying system, we can have many potential purifiers, right? So we can have more than one kind of purification, and they're all related, right? So they're related by some isometry on the environment, okay? So all purifications are related, isometry on the environment. Okay, so let's go through that. So in particular, if I have two environments, HE1, HE2, and there's some map between them, which takes me between two purifications. So psi2 is equal to V tensor the identity on HA times psi1. And if I define this as W, right, then you can check that these purifications are the same, as in they induce the same linear functional on the algebra of operators for A, right? So this L of H, which I forgot to define, I'm going to call A, big A, curly A. Then, for them to induce the same state, so I have two different pi's here, two different representations. You require the following to be the case. Like this. And this works as long as W acts as follows with respect to these representations. To a W, and in particular, W is some projection, I'll call S1, and W dagger is some other projection, S2. Then this equation works out, okay? These projections annihilate this, leave the state invariant. Okay. Now, good. So now, if we think about these projections, so these different purifications have different environments, and in particular, these projections, if you think about them, they live in what we'll come to learn to love, is the commutant of the algebra of operators. So S1 is a projection on the commutant of the algebra operators, which is all the operators that commute in this purification. So in particular, that's just V of, all linear operators on E1, tensor the identity on A, and S2 similarly lives in the commutant of this guy. Okay. So this is the commutant. It's the set of all operators that commute with the operators here. And in this case, it's really simple, okay? But one important lesson from this is that the commutant sort of depends on the environment, okay? Good. Okay, all right, are there any questions so far? Yes? Yes.
And then you're trying to purify.
Yes.
Now, could you go over this point that how the he has the commutant is dependent on the environment. That's the point that you make.
Yeah.
So because it's a finite
Correct, yeah.
And correspondingly, there will be a different operator algebra
Yeah.
for that environment.
Yeah, that's right. Yeah, that's right. And you know, they're related by this sort of isometry, this W that actually maps between two different Hilbert spaces. So, you know, you can see that W is mapping from HE1 tensor HA to HE2 tensor HA. And it intertwines the two different representations. Okay, okay, good. Now, there's a special sort of purification that is nice for various reasons. That's called the canonical or standard purification. So let's talk about that for a little bit. Okay, so in order to define it, so you know, I'm sure you've seen this before, so let me mention, this is a version of the thermophile double purification, okay? In order to define it, we think about the following structure. We think about the space, the linear space, or the vector space of matrices on HA, right? So again, these are just linear operators. They're still this L of H. They're just linear operators on L of HA. But now I'm going to think of this as a vector space. In particular, itself is a Hilbert space, okay? So this is a Hilbert space, right? And it's a Hilbert space because I can define a norm on it. And the norm is called the Hilbert-Schmidt norm. So I'm going to write my matrices as elements. I'll write as like this in sort of Dirac notation, where M here is now a matrix, right? And so I can define inner product on two matrices just by tracing over HA and one dagger M2. Okay. Good. So how do we think about this purification? Well, let's think about an operator, a natural operator, or some matrix on this thing. So, yes?
So you had capital H. If capital H is tensor product of environment and the A, right?
Where's capital H?
The Hilbert space, the full Hilbert space.
Okay, yes, curly H, yeah.
Of an environment and
Yeah.
is subsystem A. So
Yeah.
each time when you say you're using a different formatted or a different environment, you're changing the
Full Hilbert space, yes, yes. Yeah. So yeah, I should have probably said that. That's H1 and H2. Okay. All right. Okay, so now I'm picking a particular Hilbert space. And okay, so I've defined it. And one way to think about it, well, this is a matrix, right? Particular kind of matrix. So this would be some vector in my new Hilbert space. Perhaps an awkward notation, but that's how it is. And you know, because of this broad-ket notation, we can see that this is now isomorphic to a tensor product between the dual space and the original Hilbert space, right? So this is like, sorry, I should have written it this way. This is like the Hilbert space, and this is the dual space, okay? Good. Now, HA star is the dual space, and we know, again, from undergrad quantum mechanics that this is isomorphic to HA, but it's only isomorphic in an anti-linear way, and because there's no sort of canonical way to make that linear, it's convenient to actually work with this as my purification, the actual dual space, and not this. Now, often when we talk about the thermophile double, you'll try to replace this with this by making some arbitrary choice. But we don't have to do that if we just work with this guy as our purify. Okay, so that's what we're gonna do. And so on this Hilbert space, I define a representation of my original algebra, pi a. it acts on these matrices by left multiplication. Okay? And so it's easy to see what is the commutant of this. So, so in particular, so the commutant will come from the right action, right? So I'll just define another representation, pi r of a, m, just to be m times a on the right. And these actions obviously commute. You can just check that. Okay. So this is sort of my environment. These are the operators on my environment. So, you know, pi of a prime, we write it like this, is the same thing as pi r of a. Okay. It's meant to be curly. Okay. And now we can check. Okay, so now this is a representation, but we have to find a state that is the purification, and I claim that the correct state is just the square root of the density matrix D. Okay. So this is my purification psi. Right, and so you know, what I mean by that, this is a matrix, right? So this is a vector in the Hilbert space. And so I can just compute its expectation value on the subalgebra of the left action here pretty easily. I just compute pi of a root d using the rules that I just gave you. This is the right action on here. So this is a root d. And then I use the Hilbert-Schmidt norm. So this is trace root d, a root d. And then I use cyclicity of the trace to bring this around. This is just trace of a, dA. Okay? So that's the expectation value of the operators in that state. So this is a purification. Okay? Good. Now, okay, so there's a few things that happen in this purification that are useful to point out, because we're going to do this in infinite dimensions later on, and so it's a little bit smoother if we have something in mind in the finite dimensional case. Okay, are there questions? Was there? Yeah. Well, it does commute with this, right? You can just check that it commutes. So at least the commutant this is at least contained in the commutant. But yeah, you can also do some checks to make sure that it's everything. Yeah. Yeah. Other questions? Okay. All right. So. Okay, suppose, now let's suppose that D is full rank. So this is some special condition. It just means the density matrix has no zero eigenvalues, or D is invertible. And in that case, this state is special. So the state, if D is full rank, then, and in fact, this is an if and only if, the state rho, which we started with, is faithful. Okay, so what is that? So this is some condition on rho. This is the condition that if I feed in a positive operator and I get 0, then the positive operator had to be 0, right? So that's a condition, right? So it's not always true, but there's certain states where that's true. Okay, and that's called a faithful state. And so you can now check this, right? So let's just check one of the directions of this direction. So in particular, if D is full rank, let's just check that it's faithful. So we need to show that, so we need to show trace of D A plus is 0, so let's assume that. And then we can rearrange this trace just by cyclicity. We again write it in this sort of form here. Root D, A plus is a positive operator, so I can take its square root as well. I'll write it like this, and now this is just an inner product on this Hilbert-Schmidt, with this Hilbert-Schmidt norm of two things that are the same, A plus root D with root A plus root D, right? So if this is 0, then you're just by the definiteness of this inner product, that means that root A plus root D is 0. Because D is invertible, I can just kill that. So that implies that A plus is 0. Okay? Yeah. I don't know that terminology, so. Separating. You want to ask if it's the same as separating? No. Okay. Yeah, so I'm about to mention cyclic and separating, so if I don't answer your question, ask it again. Well, it's like that, but it has a different, it's basically the same, but yeah, it has a different definition, but it's essentially the same, yes. So so this is just a statement about the state, rho. So we can talk about rho independent of the purification. This had nothing to do with the purification. Rho is faithful, okay? But now let's go to this canonical purification and see what it implies about the canonical purification. And actually it means that the state is cyclic and separating, as we were saying. So let me see what that means here. So root D on this Hilbert space is, so if D is invertible, then root D is cyclic and separating for the algebra pi of A. Okay, so I always have to say which algebra I'm talking about. I need to say the state in the algebra to talk about cyclic and separating. So what is this? So let's talk about separating first. Separating. So it's separating if pi of A acting on root D vanishing implies that A vanishes, okay? So this looks very similar to the faithful condition, except we've just changed what we mean by A. So A plus, the positive operator in this case is just A dagger A. Right? So if you just take the norm of this, then you get back to this faithful condition. You just take the inner product of this with itself. It's the faithful condition with a positive operator here, which is A dagger A. So it is the same as faithful. And cyclic, if pi of A acting on root D generates all of the total Hilbert space H, right, which is this purification L of HA. And so yeah, so you can just check this because pi of A, this is A times root D, and I can just choose A to be some matrix times the inverse times D to the minus a half, okay? Where M is any matrix, right? And that's a general vector in this Hilbert space, okay? So that means that's cyclic. Yeah, so you get both of these things here. And roughly that's because in this canonical purification, things are symmetric. So if one was cyclic, the other one had to be separating. That's because of this special purification. So we'll come back to that, but yeah. Yeah. Yeah, well, so now, yeah, so if D is not invertible, then it won't be faithful, and then any purification won't be separating. Now, whether it's cyclic or not actually depends on the purification. So, you know, if we're working in this canonical purification, then it will also not be cyclic. Yeah. So, yeah. Okay, other questions? Yeah, so this is a condition that, okay, maybe from a quantum mechanics point of view seems a little bit arbitrary because, D is invertible if it has full rank, which is not obviously a condition we're interested in. It's sometimes called fully entangled. But it turns out that, well, for various reasons we're interested in this. For one, most states can be approximated by these states, so you can always work with this state, and it's quite convenient to work with these states. The other thing is we'll find in quantum field theory, you'll always have cyclic, the vacuum will always be cyclic and separating for algebras that are localized, okay? And that will be special, special situation. Okay, so the final thing I wanted to do with this purification is to talk a little bit about modular theory. So Tomita-Takasaki modular theory, which is something that I'm going to try to get to in full generality for von Neumann algebras, but here we'll just do a baby version of it in finite dimensions. Okay? Good. So let's see. Where was I? Okay, so let me just define the following operators. These are the Tomita-Takasaki modular operators. I just give you the definition in this on the canonical purification. So the first thing is this J operator. J is an anti-unitary operator, and it's just defined to take any matrix to its dagger. That's just its definition. Okay. So that's the first one, and the second one is some operator called delta, which is sort of a version of the density matrix. So the density matrix lives in this sort of the left action. But then we also include another density matrix on the right, the inverse of the density matrix, okay? So these are just two operators that we can define. And you can check that they satisfy the following things. They satisfy the following equation, J delta to the 1/2, pi of A times the state, square root of D, is equal to pi of A dagger times the state square root of D. Okay. So you can just check that. I'll leave that as an exercise, but it just follows from the equations that I've given here. The reason we write this equation is actually this is the defining equation for these operators. So you start with this equation. And that's what defines these. You split this using a polar decomposition. We'll talk about this more later. And then you get these two operators like this. Okay. The important point, so let me actually get to the point because you're probably confused why I'm introducing these things. The important point will be that in a general von Neumann algebra, these two objects are always well-defined, whereas the density matrix is not always well-defined. So the density matrix lives here, because there's another thing here. So if you like, this combination is somehow UV finite. And so, what it will turn out is that, these operators are well-defined, so they sort of play the role, they're proxies for the density matrix when we don't have a density matrix. So when we're going to talk about quantum information, we need these things, okay? And so, this is how it will be introduced. In particular, it will be introduced by this equation. Okay. And they have some other consequences that are really easy to see in this canonical purification. So the first one is, if I take J and I conjugate an element in the algebra of interest, then I just get an element in the commutant algebra, which is this right action. Like this. Get the dagger operator there. And if I conjugate delta to the power of is by an element in the algebra, I get another element in the algebra, which is just the density matrix conjugated by this thing. Right? And so these are important results that follow in general from Tomita Takasaki modular theory. They're very simple here. In general von Neumann algebras, they're very complicated. Okay, so this is the consequence. In particular, this is mapping an element in the algebra to another element in the algebra, and this is taking an element in the algebra to its commutants. Okay. Okay. All right. So let's now move to infinite dimensions. But let me see if there's any questions. Questions? Okay. Everyone's ready for infinite dimensions. Okay, infinite dimensions. Yes and no. So they're easiest to define in the canonical purification. In the non-canonical purification, you can define versions of them. They're just a little bit more complicated. And then, yeah, they're not as nice. Let's just say they're not as nice. Yeah, you can define them. Yeah, so you have these support projections that arise, and they pepper these equations in various ways. And yeah, so that, yeah. But let me also just say that as will motivate most things we're interested in are cyclic and separating. So there will be in a version of this sort of canonical purification in any case, so it doesn't matter. Yeah, it is equivalent to cyclic and separating. Yeah. Okay, it's equivalent to the existence of a cyclic and separating state. That's the right statement. Yeah. Yeah, so yeah, at this point, it can be complex, but we have to be really careful in infinite dimensions. So yeah, yeah. Then let's just say it's real. Okay. Any other questions? Okay. Okay. So all right. So let's move to infinite dimensions. So that means our Hilbert space is infinite dimensional. So the first thing we have to think a little bit about is, in infinite dimensions, we have to think about the topology on this Hilbert space. Right, so what it means for vectors to be close to each other. And so, we need some distance between vectors, and we use the Hilbert space norm for that, right? And so, for example, some sequence converges to psi if and only if this difference goes to 0, okay? So if we say the limit, if we say this, something like this is what we mean. Okay, so now in particular, the Hilbert space, as usual in this setting, is complete with respect to this metric. And we can think about things like subspaces of the Hilbert space. So you can think about a closed subspace. So a closed linear subspace. Space of H. Right. And if you have, okay, so some linear subspace need not be closed, but if it's not, then you just take the closure, right, using the topology in the usual way. And corresponding to some closed linear subspace, there's some orthogonal projection operator. So there's a correspondence between linear subspaces and projections. Closed linear subspaces, S. Right, so projection is an operator. This is an operator on H, okay? And it satisfies, S squared is S, right? And in particular, in this case, 1 minus S is also a projection, and it will kill this subspace. Okay, so that's an example of where we need to use the topology. Well, if you wrote down a projection, then it would give you the closure, right? So you can just go from the equation that defines this to see that it's automatically closed. So yeah, you'll get the closure. No, separable. Okay, so our Hilbert space will be separable. Von Neumann algebra people don't assume this all the time, and so sometimes that's a good thing, sometimes not. Mostly it's a good thing. So mostly they're sane. No, the theory of von Neumann algebras works for inseparable Hilbert spaces. There are some statements that I think I'll make that are wrong, but I actually don't really know. I have to look them up. Yeah. So that's right. And they don't often arise, but they sometimes do, yeah. Is there any other questions? It's just the Hilbert space norm. Just the Hilbert space norm. That's just, yeah. Okay. What's that?
Norm states, like
yeah, it's a usual Hilbert space.
Okay.
Yeah. So there's no zero norm space. Yeah, that's right. The inner product is definite. Yeah. Okay. Good. Okay, so now in this, we talk about, operators, okay? But previously we talked about linear operators. Now we have to be a bit careful because we're in infinite dimensions. So the right thing to think about are bounded operators. So I'll denote that B of H. So these are, this is a subset of linear operators. Well, it's actually, yeah. So yeah, let me just say it this way. So bounded operators are operators M on the Hilbert space. And they're bounded because their operator norm is finite. That's all it means. Less than infinity. And the operator norm, in general, is just defined as follows. You take M, you act on all states in the Hilbert space, and you divide by the norm of that. Okay, so that's the operator norm. And yeah, so we're looking at operators that have that are bounded. Okay, so this is convenient because this is now an algebra, right? This is an algebra. It's one of these star algebras, and actually it's going to be an example of a von Neumann algebra, which we'll get to. Okay. This is what we're interested in. This is all observables. But of course, now we want to talk about Alice's observables. And if you like, this is now including the environment. Okay, so we want to think about some subset of, or some subalgebra of operators. So we're interested in some subalgebra A of B of H. Okay, and at this point, I've dropped this pi notation, right? So previously, I had this sort of representation pi of A, and the reason I'm dropping it is just because often when we talk about von Neumann algebras, at the end of the day, we have in mind a very specific representation. So we'll just be in that representation. That's a physical statement as well. So many of the situations we're in, we're just in some fixed representation. Okay, but you might also want to add something else, in which case then you have to think about this pi. But for now, we're dropping the pi. It's not there. We're just in some fixed representation. Okay, so we're interested in subalgebra of operators here. So it's an algebra. It's actually a star algebra, which again, remind you, just has products and sums in A, and the dagger is in A. Okay. And not only are we interested in that, we're also interested in the commutant, which is the environment, right? The commutant so A prime is just the set of all operators A prime such that A prime commutes with A, right? So that just means commutes with all operators in A. I'm just being quick with my notation, right? So this is the commutant. This is the definition of the commutant. Okay, and we denote it this A prime. Okay. All right, so that's what we're interested in. So on A now, let's go back to A. We're interested in, A should be somehow closed in some topology. So this is just like our Hilbert space is closed in the metric. The algebra of operators should be closed in some topology. And there's various things we can choose, okay? So there's various options. So the first option is one, we can close A is the same as the closure with respect to the operator norm. So what does this mean? So this notation just means closure in the usual sense of topology. And the operator norm is what's defining our topology. Norm defines the topology on the space of operators. Okay, so that means, what that really means is that, if we have some sequence of operators, and say this is in A, that's the other way around, in A, and it converges to some operator, and this is in just some operator, so it could be B of H in this sort of total Hilbert space, some operator on the total Hilbert space. And what we mean by this line here is the limit as n goes to infinity of an minus a using the operator norm, which I've defined here, is 0. Okay, so we take a limit using the operator norm. And if we had a sequence in A, and A was closed, that means the limit has to be in A. So this is if and only if. A is in A. Okay, so this is what we mean by A is closed. So sequences in A that converge to some operator, the operator they converge to also has to be in A. Okay, so that's the usual topological notion. Okay, so questions about this? Okay, so this thing that I've just defined is called the C-star algebra. Okay. Now, so just a comment is that usually C-star algebras are not defined in this way. They're defined more abstractly without any reference to a Hilbert space. And then you usually derive a Hilbert space in some way. But here I can still talk about C-star algebras as subalgebras of B of H, that's fine. Okay, and so that's what I'm doing here. So that's one option. The other option is the thing that gives us von Neumann algebras. And yeah. The C-star algebra is not a Hilbert space here, no. No, it's just operators on a Hilbert space.
Are you going to use the inner product from B of H?
No. Forget that. Forget that, yeah. Yeah, it's not, yeah. So in infinite dimensions, you can't really do that. Yeah. So the canonical purification is going to be slightly different to that. Yeah. It's just, yeah, it was convenient just because, it's simple to start with. But yeah, it's something we can't quite do. We'll have to use sort of the full thing of modular theory to get there. Okay. Other questions? Okay. So the other thing we need is, so the other option is we can close. So A is equal to itself under the closure with respect to something called the weak operator topology. So this is closed in the weak operator topology. And so, to define that, you similarly need to define what I mean by converge. So it means that, if I have a sequence of operators converging to A in some limit, in the weak operator limit. So this is also sometimes denoted like this. So this is some notion of convergence, and it's defined by the fact that matrix elements, fixed matrix elements, should converge. Okay? So for all psi phi in the Hilbert space. So we fix any two vectors in the Hilbert space, this should converge, and that should be true for any two, right? Any two such psi phi. And so, this is like matrix element conversions. That's what we mean. We're just taking matrix elements and we make sure that those converge. Right. So there's So now you can sort of think of a topology that's defined by this notion of convergence, and that's what we mean by the weak operator topology. There's a subtlety here in that this doesn't actually define the topology quite. We can still talk about weak operator convergence of sequences, but it's not good enough to generate all operators in the closure. So you can't just like take all operators that converge in a sequence like this. You have to do something else. You have to introduce something called a net. It's quite complicated. It's just a generalization of a sequence. But it's necessary because this topology is not determined by a metric. Okay, so it's determined by these matrix elements, so that makes it a bit more subtle. Now, nets are something that I've barely ever dealt with, so in some sense you can get away without it, I think. But it may come up. You should, in which case I'll let you read about it by yourself. Okay. So this is roughly sufficient. So this A is a weak operator closure, defines a von Neumann algebra. Okay? Okay. It's still working. Okay, questions? Yes? Yeah, so C-star algebra, so all von Neumann algebras are C-star algebras, but not the other way around. Okay? So, and the reason for that is that okay, let me just say a few more things here. Okay, good. There's another, sorry, yeah, I'll get back to that question. Just let me say one more thing. There's another notion of convergence, which is called the strong operator convergence. And this is defined by not matrix elements, but just acting on an arbitrary state in the Hilbert space. That should go to 0 for all psi in the Hilbert space, right? So it's just a slightly different notion than weak operator convergence, but it gets its own name and it has its own topology. And so we actually have the following order on topologies. So this is the topology defined by the norm. This is where we get C-star algebras. This is where we get von Neumann algebras. And so this order on topology just means that more sequences converge here. And less sequences converge here. So that means this thing will always, the closure will always result in a bigger object, right, than the closure under this. And it also means that all von Neumann algebras are also C-star algebras. Okay? Good. It turns out that even though the topologies are different, the closure of a star algebra under the weak and the strong operator topology gives the same thing. So you could have also defined it using the strong. That's okay as well. Okay, so now one reason I can be a little bit glib about this topology is there's a beautiful way to define a von Neumann algebra just algebraically. And this goes under the name of the von Neumann bicommutant theorem. So, yes. Yeah, so good. Yeah, so there's some physics here. There's some question about what we should care about. Yeah, I think physically this is the kind of thing that we can access in an experiment. So you can use some physical words to motivate this weak operator convergence. It's the matrix elements that we can measure, right? The norm of the operator is kind of hard, right? So this is the thing that we would be able to measure. And so that means that, if we have some approximation to our algebra that's not everything, we can still get matrix elements of everything to some good approximation. That's what that means. Okay, and so that seems like a physical thing. There's a mathematical motivation as well, which is the von Neumann algebra theory is beautiful and has all these nice results. Okay, so say again?
None of them contains the identity.
So von Neumann always contains the identity. The C-star algebra need not. Yeah. What's that? Identity operator is a great bounded operator. Look at the definition. Yeah, so its trace is not bounded. It's not trace class, but yes, yeah. This is 1. Its norm is 1. Okay, good. Okay, so bicommutant theorem. Okay, so let's just start off by considering some set of ops, which satisfies S dagger as S. So if I take the dagger of each element in the set, I get back itself, right? So this is some set of operators. Then the bicommutant theorem, or one of the consequences, or one of the statements, S prime is a von Neumann algebra. Okay, so when you take commutants, you always get a von Neumann algebra, as long as you started with a set that satisfies this. And you can see that, it's not hard to see that. So in particular, you can see that if A1 and A2 are both in this set, then their product is in the set just by using, like the commutation relation for the product of operators. So this is also an S prime. So it's an algebra. So that's clear. Then you just have to show that it's closed in the weak operator topology, right? And so you make some argument like this. Let's see. Yeah. We suppose we have AN going to A, where A is in the these things are in S prime, the commutant of this set. Then we just have to show that A is also in the commutant of this set, where this is going in the weak operator topology, right? So the weak operator limit. So we just take matrix elements of the commutant of AN with any element in the set S, in the original set S, like this. So we know that this converges because this is just a matrix element, okay? It's a matrix element of some set of operators. It's two matrix elements, right? But each of them is just a matrix element, so we know that by the weak operator topology, it has to converge to this, right? And so if this was 0 to begin with, then this has to be 0 at the end, right? So that means that matrix elements of this have to vanish, of this commutant has to vanish, and that actually implies the full thing has to vanish. So that is true, and so that means A is in S prime, and so S prime is closed under the weak operator topology, so it's a von Neumann algebra. Okay? Yeah, good. Because I also need A star to be in S prime, and that won't be true if I didn't start with something. Yeah. Okay, so good. And notice that you always get the identity. The identity, you always get the identity under this argument. So the identity is always in the von Neumann algebra. Okay, so now we can take two commutants, and that's also von Neumann algebra. And this is the von Neumann algebra that's generated by S, right? So you can think of this is the minimal von Neumann algebra that contains S, the smallest von Neumann algebra that contains S. Right, and so our condition for a von Neumann algebra is going to be simply that the W commutant is A, right? So the W commutant gives you the closure, which for a von Neumann algebra is itself. So that's just that's the bicommutant theorem. So that's kind of a very simple algebraic way to see this. Okay, good. Okay, so let me say a few consequences of this. Any questions? Yes. Say again?
Why did you restrict to weak operator?
Well, I can prove it for the weak operator topology, and since it's the weakest, that's all I need to do. So of course, as I said, it's a C-star algebra also. So yeah. Okay, good. Now, okay, some things about this. Some things. Okay, firstly, okay, it's not hard to see that if I take the intersection of two von Neumann algebras, it's also a von Neumann algebra. And then there's also a notion of combining. So this is like taking the intersection, and there's some sort of union notion. So there's the von Neumann algebra generated by the two von Neumann algebras, and that's just defined by taking the union, which is a C-star set, and taking the double commutant. Okay, so that's what I mean by the thing generated. That gets this sort of V symbol. Okay, and then you can prove, it's not hard to prove that the following relation is true. AU AT prime is the same as A1 prime intersect A2 prime. Okay, you can check that. And one more thing, it's also not hard to see if I have two subalgebras. So A is a subalgebra of B, then B prime is a subalgebra of A prime. Okay. Now there's an important subalgebra of A itself, which is called the center. So the center of A is just defined as the intersection of A with its commutant. Okay. So because it's intersecting with its commutant, all operators in Z of A commute with themselves, right? So this is actually a special class of von Neumann algebras, which is called a commutative von Neumann algebra. And there's a whole, literature on this, and in fact, it's equivalent to sort of probability theory. So this is just the same as probability theory, sort of measure theory. And so in some sense, like quantum mechanics is the sort of non-commutative measure theory in this sense, right? So it's a non-commutative von Neumann algebra. A special case is this commutative. And so this is sort of classical probability theory. And so you see, like, if there's a center, the algebra you're interested in has a center. This is some classical probability thing. So it's something where we might have a system which has some classical parts to it and some quantum parts to it. And we can model that using the center. Okay? Yeah. Now, a von Neumann algebra factor is one where Z of A is just multiples of the identity. So that means it's trivial. It's like the smallest von Neumann algebra you can have. And this is what defines a factor. And this is sort of like a decomposition. So in particular, all von Neumann algebras can be written as a direct sum over von Neumann factors. Right? So if you know everything about all the possible factors, then you sort of know everything about all von Neumann algebras. So you sort of restrict to factors and you're good, at least mathematically. Physically, there's also often reasons to restrict to factors. Okay, so factor just means this trivial center. Okay. Yeah.
Sorry, could you say again why studying factors is enough?
Yeah. So I'll say it a little bit more detail. Yeah, I'll only say it by example, but basically, A can be written as a direct sum over factors. Right. So you can decompose it. It's like a fact. Yeah. But let me give an example of that. And this example defines all possible type 1 von Neumann algebras. Right, so I haven't really got to the classification yet, but just by exhaustion, this defines what I mean by type 1 algebras. So they're direct sums. So A is a direct sum over some environment, like we had in the first part of this lecture, times B of some HAI. And there's a sum, there's an index I for each of these. Okay, so that's the general case where we have some direct sum where this indicates that it's not a factor. If it was a factor, this would go away and we'd be exactly in the setting that we started with, Alice in her environment. Okay, and in this context, you can find commutants and so forth. A prime is also a direct sum of B of H on the environment, tensor the identity for Alice, okay? And then the center, A intersect A prime, is just the direct sum over complex numbers Zi, where Z is a complex number. And really what this means in some block notation, because we're doing direct sums, the Hilbert space is a direct sum, and the operators on the Hilbert space have this block decomposition where we put a Z1 here, the identity on E1, A1, Z2, identity E2, A2, so forth, down the diagonal, right? And so these obviously commute with each other. You just have different complex numbers here, and that's the center. Yeah. Yeah, it can be infinite. It can also be an integral. I just didn't want to get into that case. Yeah, it can be a direct integral, which makes it complicated. But yeah. Okay, good. All right. And yeah, good. Okay, so now, So now let's focus on factors, and we'll try to give some classification of possible factors. So focus on factors. Right, so the center vanishes. The center is trivial. Okay, so to classify the possible von Neumann algebras, the original classification, we focus on the projections in the von Neumann algebra. So we're going to be interested in projections. So sort of EI that come from A, from the algebra, okay? And what we want to do is define some notion of size of projection. We want to compare the sizes of two different projections. So to do that, we define an equivalence class on projections. So in particular, so we define some equivalence class where E1 is equivalent to E2 in the von Neumann algebra A. I won't say that, but it's implicit. If there exists some partial isometry, V in A, partial isometry in A, such that E1 is the initial support and E2 is the final support of this partial isometry. Okay? So what does this mean? Well, let me give an example. And of course, you know, what are we going to do? We're going to do it in finite dimensions because that's the best way to think about things for now, at least. So E1, for example, can be some identity on the environment, it has to be that, times some projections onto some orthogonal subspace defined by some set of orthogonal vectors, 1 up to m. Right. So this is on H, E, I don't need a 1 there, no I don't, yeah, E times HA. Okay. And you know, K, the dimension of this guy, K, is bigger than or equal to M, right? And E2, if there's an isometry like this, that actually means that E2 has to have the same form with just another set, orthonormal set of vectors, okay? Right, and so where V here is easy to write down, it's just 1 on the identity, on the environment, 1 prime, 1, 2 prime, 2, etc., M prime, M, okay? And so this is just a change of basis, right? So we're saying they're equivalent because, you know, they're essentially the same size, right? They are the same size, they have the same number of terms here. So this, yeah, so E1, E2, equivalence on the size of E's. Okay. Now, given this, we can define.
Could you clarify? So this is only for finite algebra.
Well, the example that I gave is only for finite algebras. This is a general statement. Yeah. So we'll see how that works now. So that's a notion of infinite projection. So yeah. So we need so. Given this notion, so this was just an example, right, where we can easily visualize. But more generally, we can just define what we might mean by an infinite projection. As a projection, so E this is an infinite projection if E is equivalent to some F, where F is a sub-projection. So being a sub-projection, you can think of it in terms of this sort of equivalence between projections and subspaces of closed subspaces of the Hilbert space. So that just means that HF is a closed subspace of HE, where these are the projected Hilbert spaces. Okay, and so that's what I mean by that. It's also, you know, an operator inequality in the usual sense as well. But you can think of it just like this. Okay, so an infinite projection is one that's equivalent to a sub-projection. And one way to think about this is that, you know, this is a sub-Hilbert space, but if they're both infinite dimensional, they're sort of isomorphic to each other, right? Because all infinite dimensional Hilbert spaces, as long as they're separable, are isomorphic to each other. So I can find such a V dagger V, that does this in this case, as long as it's infinite. Okay. Okay, and so that's an infinite projection, and then a finite projection is the complement of this, so all the rest. It's just one that an isometry that has a V dagger V is not the identity. Okay, usually an isometry is one where V dagger V is the identity, and V dagger is a projection. This has both. Yeah, they're both projections. Yep. Okay, so this is important. So we have this notion of infinite projection, and this is what's essentially going to give us the classification. There's one more notion. So we have infinite, finite. Let me just go over here. A minimal projection is one that just has no sub-projections. So there's no sub-projections. And so an example of a minimal projection, e.g., is just the identity on E, tensor 1, 1. There's no strictly less than projection. So there's no projection that's strictly less than E. So this has to be strictly less than. This is not equal to. No, I don't know. Yeah, we can call it a projection and then get rid of that case. Yeah, it's not included in this. Yeah, I guess non-trivial projections. Yeah, yeah. Okay, so good. Okay, so now I can start filling out this table. Okay, so let me write, and then I'll sort of populate this. So type 1K is the first kind. So I should have said 1 is a projection, an example of a projection in the algebra. Okay, and type 1K is such that 1 can be written as a sum of minimal projections, minimal, mutually orthogonal projections, and there's K of them, right? K, yeah. And that defines this index K, right? And so this is going to be our example of HA where the dimension of HA is K. Right, so these, where the minimal projections are just some basis of this Hilbert space. Tensor the environment. Okay, so that's type 1. This also includes the case K is infinite, is that if there's an infinite number of these. Okay. Okay, type 2-1. Okay, so yes, it doesn't have to be, it can be uncountably infinite. But then in that case, it's not represented on a separable Hilbert space. So we can get rid of that by saying separable. Yeah. Yeah. Okay, so type 2-1. This case is when 1 is, right, so this is type 1, and then if it's not type 1, then we have the following. 1 is a finite projection. In particular, there's no minimal projections. there was a minimal projections, you can actually show that it has to be type 1. And type 2 infinity, 1 is an infinite projection, so it's equivalent to a subprojection. But there exists finite projections. So not all projections are infinite, but the identity is. And then the final case is type 3, where all projections are infinite. Yeah, there's no minimal projections, yeah.
So if there exists a minimal projection,
Yeah, that's right. Yep. Yeah. Okay. So now I can start filling out this table. So in type 1 we have a minimal projection, and there's finite projections. Right. That's just the sum of the minimal ones are finite. Type 1 infinity, there's minimal projections, and there's infinite projections. There's finite and infinite. In type 2.1, there's finite. Type 2 infinity is finite and infinite. And in type 3, there's infinite. Okay. Now, one thing that I can say already is that this tells us a little bit about the states that we can have on the von Neumann algebra. So in particular, a minimal projection, remember, was this sort of E tensor this, right? So one of these states here. And so that's a pure state from Alice's perspective, right? So Alice has a pure state. So this, type 1, you can have pure states. Type 1 infinity, you can have pure states. But you can't have pure states on any of the other ones. Okay? There's always an environment. You can't get rid of the environment. Okay? Okay. Good. So, how is my time? Okay, I might take 10 minutes. You said 10, sorry. What's that? Okay, yeah, there's a natural point. Hopefully I get there. Okay, all right, so this is in terms of projections. So let's say a little bit about states in von Neumann algebras. So as I sort of motivated at the beginning of this talk, a state is just a linear functional. So it's a map between A and numbers, right? Of course, it should be positive because we need some notion of positivity. When acting on a positive operator, it should spit out a positive number. Now we can add qualifiers to this notion of a state. Right, so if you open up some operator algebra paper, you'll see these 5 qualifiers that run before a state, the notion of a state. And so this is some of the things you can add. So the first one we've seen already, which is faithfulness. Right? So as in, not all states need to have these properties, but you can include them or not, depending on what you want to do. So rho of A plus is 0. Means A plus is 0. So that's the faithfulness condition. It should be appropriately continuous. Right, so we have some notion of continuity on A, so that means the states should have some notion of continuity. Otherwise, it's not sort of intrinsic to that operator algebra. So we need to make sure that it has that right notion. And actually, this depends on the algebra. So if we go back to C-star algebras, the natural notion is just that rho should have a nice norm, where the norm is just given by the norm on linear functionals, which is defined as follows. Sup over all A that you can put into the linear functional, rho A over the norm of A. And so if this is finite, then it's continuous. It turns out that this is always finite because of this positivity condition. You can show, and I'll leave it as an exercise, that the norm, this norm rho, is just rho of 1 because of positivity. So this is for C-star algebras, but for von Neumann algebras, there's a more subtle continuity that you have to add, which is known as so normal. So what does normal mean? So normal means if I take this linear functional and I think of it as a map between A, and I restrict to algebra elements that are bounded. So just bounded sets will do, but bounded by 1 is okay too. So if I take that and I restrict to bounded elements, and I think of this as a map, then it has to be a continuous map. Equipped with the appropriate topology, right? The topology, which in this case, we're talking about von Neumann algebras, it's the weak operator topology. Okay, and that's what it means to be normal. Well, normal technically means this and positive. Okay, so when you see normal, it means positive and continuous in this sense. Right, and then a final thing that you might add is something called tracial. So tracial, a very special class of states. So they usually get a different symbol. Instead of rho, I'll call them tau. So rho is now tau. And tracial states have this cyclicity property of a trace. Okay. So in finite dimensions, obviously, a tracial state itself is a trace. In fact, you should think of a tracial state in finite dimensions as a maximally mixed state, because the density matrix is then the identity, and so the state is a trace up to a constant. So it's like a non-normalized trace, or a funny normalized trace. Because I haven't said anything about the normalization here. Okay, and so the final, thing that we have to talk about in terms of this classification is what kind of traces you can have on these von Neumann algebras. And it turns out, just from understanding these projections a little bit more than I've told you, you can classify the possible traces you can have on these von Neumann algebras. And these traces, well, okay, let me say a few things. So I'll just make the claim that type 1K, 2,1 have a unique normal, faithful, here we go, trace. Tracial state, let's say it that way. And so that sort of is unique to these guys, where they're the von Neumann algebras that don't have an infinity on the bottom here. So that's first claim. Type 1 infinity, 2 infinity have a unique non-normalizable normal tracial. Now I want to say state, but it's not actually a state. It's a more generalized notion of a state called a weight. And that's something that I will not have time to define, but it basically means it's non-normalizable. So yeah, it's something you can't ever normalize. There's just no way to normalize it. And a good example of this is just the trace on this guy. Well, this guy, what is this? Well, these are just bounded operators on an infinite dimensional Hilbert space, separable Hilbert space. And then I just have the trace, right, on that thing. And that trace is well defined on some operators, but it blows up on many operators as well, and that's what it means to be non-normalizable. In particular, trace of the identity is infinite, okay? And so this sort of is special for these types. And then the final thing is type 3 have no traces in either of these senses. Okay, so that means we can add to this list, and that's probably where I'll stop. Okay, so traces. This has a trace. This has a trace. Trace does not. And you should think of traces. You know, in this type 1K case, the trace. Well, what is it? The trace is just a sum of, from 1 to k, n is 1 to k, n like this, divided by k, right? And this division by k just means that trace of 1 is 1. That's often how we normalize it. But yeah, so this is the trace in that case, and what is this? This is just a maximally mixed state. That's all it is. Okay, so if I think about this in terms of the density matrix, it's just proportional to the identity. So this indeed has a maximally mixed state. This also has a maximally mixed state. This has a sort of non-normalizable maximally mixed state. Non-normalizable. Similarly, this has a non-normalizable one. And this does not have a maximally mixed state. Right, so you can think about this classification physically as the kinds of states that you have on the von Neumann algebra. The kind of states that you can have on the von Neumann algebra. Okay? And so I think that's sort of the physical way to do it. The mathematical way is here, but this is the physics. And yeah, and so we'll see examples of these. Yeah, let me say one more thing, which is examples. Very physical examples of all of these things. Examples, where did it go? Yeah. Examples. Type 1, of course, is just, you know, usual quantum mechanics that you're probably familiar with. Let me just say familiar quantum mechanics. Type 3 is observables in some subregion of quantum field theory. And type 2, which is a sort of relatively new addition to this dictionary, subregions in semi-classical quantum gravity. Okay, and so let me finish there. And yeah. That's type 1. That's B of H, it's type 1. Yeah. So I probably didn't emphasize it enough, but type 1, B of H is always type 1. So if you have all operators on your Hilbert space, it's type 1. So yeah, you have a situation which is maybe a bit weird. It sounds a bit weird, but it's not actually, where you have type 3 von Neumann algebra that sits inside a type 1. That's fine. You mean on everything? Yeah, it'll be type 1. Yeah. Other questions? Yeah, so the projection is usually the way you define it, the original way. Yeah, well, actually, no. I mean, at the same time, so you use then the projections to construct these traces, right? So these traces that I claimed are unique, And that proof of that comes from understanding the projections. Basically, you define the trace on the projections, and based on that, yeah, you can construct these traces and show that they exist and that they're unique, up to scale.
Any other questions? Okay, let's thank Tom again.